Ever wondered how data is organized in your computer? Well, it's not magic, but it's something called data structures. Let's dive in. Data structures, quite simply, are methods of organizing and storing data in a computer. But why is this important? Picture this. If you had to find a specific book in a library without a catalog system, daunting, isn't it? That's where data structures come in. They're like the catalog system for your computer, allowing for efficient access and modification of data. Imagine you're a chef and data is your ingredients. Just as chefs organize their ingredients for easy access and efficient cooking, programmers use data structures to manage their data, reducing processing time and improving performance. But it's not just about speed. Data structures also provide a level of abstraction, hiding the complexity of the underlying system. This makes them reusable across different programs, boosting efficiency and productivity. There's a broad spectrum of data structures, each with its own strengths and weaknesses. Some are simple, like arrays, which are like egg cartons storing elements of the same type in neat little compartments. Others are more complex, like trees and graphs, which are akin to family trees or city maps, representing hierarchical or interconnected relationships between data elements. In essence, data structures are the backbone of data management and organization in computers. So, the next time you're browsing your photos, playing a game, or even sending an email, remember, there's a data structure working behind the scenes, making it all possible. Data structures are not all the same. They come in two main flavors, linear and non-linear. Now let's put on our computer science hats and delve into these two classifications. Linear data structures, as the name suggests, store data in a line or sequence. Think of it like a row of ducks. Each duck follows the one before it, and there's a clear beginning and end. This linear arrangement makes these structures ideal for tasks where data needs to be accessed in a specific order. It allows for easy insertion and deletion operations. Examples of linear data structures include arrays, linked lists, and queues. Each has its own unique features, but they all share this linear organization. On the other side of the spectrum, we have nonlinear data structures. Unlike their linear counterparts, these don't follow a straight line. Instead, they store data in a hierarchical or interconnected manner. Picture a family tree or a web of interconnected nodes. This allows for more complex relationships between data elements. It's like the difference between a single-track railway and a bustling metro system with various interconnecting lines. Nonlinear data structures include trees, graphs, and hash tables. Now, you might wonder, why bother with different data structures? Well, it's all about efficiency. Depending on the problem at hand, one data structure might allow you to solve a problem more efficiently than another. It's about picking the right tool for the job. So whether your data is sequential or interconnected, there's a data structure designed to handle it. Remember, understanding these structures is the first step towards designing efficient algorithms and optimizing software performance. Now, let's dive a little deeper into linear data structures. Linear data structures are so named because data in a sequential order, making them an ideal choice for scenarios where access to data elements needs to follow a specific sequence. There are four primary types of linear data structures: arrays, linked lists, queues, and stacks. Let's start with arrays. An array is a collection of elements of the same type, stored in contiguous memory locations. Each element can be identified by an index or key, which represents its position in the array. Because of this, arrays provide quick access to elements but can be inefficient when it comes to adding or removing elements, as this often involves shifting other elements to maintain the array's contiguous nature. Next up, we have linked lists. Unlike arrays, linked lists store elements in separate nodes, each containing the element and a reference or pointer to the next node in the list. This structure allows for dynamic insertion and deletion of elements, as it only involves updating a couple of pointers. However, accessing a specific element in a linked list can take longer, as it involves traversing the list from the beginning. Moving on to queues. A queue is a first-in, first-out, or FIFO structure. This means that the first element added to the queue is the first one to be removed. Queues are commonly used in scenarios where order of processing matters, such as in print jobs or task scheduling in computer systems. Finally, we have stacks. A stack is a last-in, first-out, or LIFO, structure where elements are added and removed from the top. Stacks are particularly useful in scenarios where the most recent data is of the highest priority, such as in undo operations in a text editor, or in managing function calls in a program. Linear data structures, with their straightforward sequential nature, are the workhorses of many computer programs. But what if your data isn't simple or sequential? Enter nonlinear data structures. These structures are built to handle data that isn't necessarily in a linear sequential order. They allow us to represent more complex relationships between data elements. First up, we have trees. A tree is a hierarchical structure where each node can have multiple child nodes. Think of it like a family tree, where each person can have multiple children, and those children can have children of their own. This makes trees excellent for representing hierarchical relationships, such as file directories on your computer. Next, we have graphs. A graph is a collection of nodes connected by edges, representing relationships between data elements. Graphs can be used to model many real-world situations, from representing networks, like social networks or web pages, to mapping routes for GPS systems. The power of graphs lies in their ability to model complex interconnections. Lastly, let's talk about hash tables. A hash table is a data structure that implements an associative array, a structure that can map keys to values. Hash tables use a hash function to compute an index into an array of buckets or slots from which the desired value can be found. They're incredibly efficient when it comes to inserting, deleting, and searching for data, making them indispensable in database indexing, caching, and more. So, as you can see, nonlinear data structures offer a lot more flexibility when it comes to organizing and representing data. They allow us to model complex relationships and handle various types of data in an efficient way. Nonlinear data structures, with their ability to represent complex relationships, open up a world of possibilities for data organization. So, there you have it, a quick tour of the world of data structures. We've explored the landscape of these crucial components in computer science that are working tirelessly behind the scenes, facilitating efficient data management, organization, and algorithm optimization. We've discussed linear data structures, the orderly folks that store data in a sequential manner. They make it easy to perform insertions and deletions, with prime examples being arrays, linked lists, queues, and stacks. Arrays, for instance, are neat collections of elements of the same type, all lined up in a row in contiguous memory locations. Then there's the linked list, a dynamic structure that links elements together with pointers. Not to be outdone, we also delved into nonlinear data structures. These are the structures that store data in a more complex, hierarchical, or interconnected manner, allowing for more intricate relationships between data elements. Trees and graphs exemplify these structures, with a tree being a hierarchical structure with nodes branching out to multiple child nodes, and a graph being a collection of nodes connected by edges, representing relationships between data elements. Each of these structures, be they linear or nonlinear, serves a specific purpose, and understanding their functionality is key to efficient data handling and algorithm design. They are the unsung heroes of computer science, the backbone of software performance optimization. So next time you use your computer, remember it's the data structures working behind the scenes that make it all possible. Understanding data structures is fundamental for designing efficient algorithms and optimizing software performance.